Section 3.8, Exponential Growth and Decay. This is a topic that you will see discussed again in Calculus 2 and Math 84. It also helps to see the connection between what we have been doing with derivatives and what's also going to come later in this class. So first, let's say that y equal f of t represents the number of individuals in a population. It seems reasonable that the greater that f of t is, then the greater its rate of change f prime of t will be. For example, just think of human population on Earth. As the number of people increase, then the rate and change of population will also increase. Or a little more relevant to our current situation, with a virus, with more people infected, the greater the rate of change in infection will be. So what this means is that the derivative of the function f of t is proportional to the original function itself, which means dy dt, the derivative of y with respect to t, is equal to k times y, where k is the constant of proportionality and k is just some constant. If we have that k is greater than 0, meaning k is positive, then we have that the derivative is also positive. The reason for that is that the original function y was already positive in itself because it is measuring a count, a population count. Thus, the rate of change is positive, and it means that the population is growing. If we have that k is negative, then that means that we have decay instead of growth. The equation above, meaning the one involving the derivative, that's called a differential equation. It's an equation that involves the derivative of a function and the function itself. You're going to see more of those in Calculus 2 and also in Math 84, which is after Calculus 3. So now, this sort of equation would have solutions, and those solutions are actually functions. So can we think of a function that works as a solution for the equation that I circled up there? What this means is, can we think of a function that we've seen whose derivative is a constant multiple of itself? And the answer to that is the exponential function. For example, if we say that y is equal to c times e to the kt, then by the chain rule, the derivative y prime is equal to k times c times e to the kt, which just ends up being k, the constant of proportionality, times the original function y. Notice also that if we put 0 in for t, then y of 0 is just that constant capital C, meaning the initial amount is c. Putting this all together, we get this theorem. The only solutions to the differential equation dy dt equals ky are the exponential functions y of t equal y of 0 times e to the kt. Now we'll just look at two examples to get a little bit of a better understanding of these exponential functions. So first, radioactive decay and half-life. Radioactive substances decay at a rate proportional to the remaining mass. Similar to what we saw above, the mass decays exponentially, and the remaining mass can be found at any time t with the function m for mass, m of t equal to m sub 0 e to the kt, where m sub 0 is the initial mass, what we started with, and k is a negative constant. That's our decay rate. Oftentimes, physicists express the rate of decay in terms of half-life, the time required for half of any given quantity to decay. Example. One of the radioactive materials released in the Chernobyl explosion is cesium-137, which has a half-life of 30 years. Part A, a sample of cesium-137 has a mass of 100 milligrams. Find a formula for the mass of the sample that remains after t years. Then Part B, find the mass left in 2020, which is 34 years after the explosion. And then Part C, when will the mass be reduced to 30 grams? So first of all, for Part A, we are going to use the equation that we have up above. So we can say m of t equal to m sub 0 e to the kt. We already know that the initial amount in our sample is 100 milligrams, so that means we can just replace our initial amount with 100. And then all we are looking for to answer part A is just what is that constant k, which we know should be a negative number. So the way that we can figure this out is by using the half-life. What this means is after 30 years, half of the material is left. So that means that m of t, the mass at time 30 years, would be 50, half of 100. And you can see that a lot of these problems now are really just exponential problems that we could have seen in a pre-calculus class. We really only needed calculus just to find out what the solutions are to get our equations to start with. So this turns into 50 divided by 100, or 1/2, is equal to e to the 30k. And we just need to get k all by itself. The way that we would do that is use the natural log function. So natural log of 1/2 is equal to the natural log of e to the 30k. So then simplifying, we can bring the exponent inside the natural log down as a multiplier. So we would have natural log of 1/2 is equal to 30k times the natural log of e. But that just means 30 times k, since the natural log of e is 1. So this means all I really have is the natural log of 1/2 equal to 30 times k, which means that k is the natural log of 1/2 divided by 30. So what you can actually see is that this constant of proportionality is really just the natural log of 1/2 divided by 30. So if you're thinking of anything with half-life, that constant of proportionality can always be found this way. It's the natural log of 1/2 divided by what is the time for the half-life. So we'll just pop this into a calculator. We're going to find out that k is going to be negative, mainly because the natural log of 1/2 is negative. So natural log of 1/2 divided by 30, we can approximate this to negative 0.023 for k, which means that our answer for part A is really just m of t equal to 100 times e to the negative 0.023 t. So then part B, find the mass left in 2020, so 34 years after the Chernobyl explosion. This really just means calculate m of 34, which would just be 100 times e to the negative 0.023 times 34. So 100 times e to the negative 0.023 times 34, and that gives us approximately 45.749, and this would be milligrams. Which should make sense. 34 years is more than 30 years, so we should see that more than half of this has gone. And then finally, part C, when will the mass be reduced to 30 milligrams? This is a question about time, since we are asked about when. So this means that the amount is 30, and we want to find t. So this doesn't mean that we're plugging in 30 into our equation, which should make sense because that would actually be very easy to solve. If the time was just 30 years, we know it's exactly half. So this is the opposite of that. This means that our amount, m of t, is 30, and we need to set our equation 100 e to the negative 0.023 t equal to that. So this is similar how we solved part A. We just divide both sides by 100. So 30 divided by 100 is really 3/10. Take the natural log of both sides, so ln of 3/10. And then the right-hand side, similar to what we saw in part A, will just really be the exponent after we took the natural log. And so then we just need to divide the natural log of 3/10 divided by negative 0.023. And that gives us approximately 52.347 years. For our other example, we're going to look at what's called Newton's law of cooling. This law states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings. The same also applies to the rate of warming. Symbolically, this gives us dt of dt is equal to k times capital T minus capital T sub s, where capital T sub s is the surrounding temperature, k is a constant, and temperature, capital T, is a function of time, lowercase t. Since this is something that can signify either cooling or warming, this could actually be an exponential growth or decay function. For our example that we're going to look at, we're going to stick with decay and we'll look at cooling. A bottle of soda at room temperature, 72 degrees Fahrenheit, is placed in a refrigerator where the temperature is 44 degrees Fahrenheit. After half an hour, the soda has cooled to 61 degrees Fahrenheit. Part A, what is the temperature of the soda after another half hour? So it's already passed 30 minutes and that temperature was 61 degrees. What will be the temperature after another 30 minutes? And then part B, how long does it take for the soda to cool to 50 degrees Fahrenheit? So with the concept above and the information that we were given, the differential equation that we can start with is dt dt, meaning the derivative of temperature with respect to time, is equal to a constant k times capital T, the function for temperature, minus 44, which is the surrounding temperature inside the refrigerator. To make this easier, we're going to let y be equal to capital T minus 44. When we do that, we can then actually take the derivative of both sides with respect to lowercase t. And just using the ideas of implicit differentiation, this means I get dy dt on the left, and then d capital T dt on the right. So actually those derivatives are equal to each other. So thus the differential equation that we had can just be written as y prime equal to k times y, which we already know has a solution by our theorem. Y is equal to the initial y value times e to the kt. So first of all, we'll find the initial y value. Since we said that y was equal to capital T minus 44, then the initial y value, y of 0, is just equal to the initial temperature minus 44, which means 72 degrees minus 44 degrees, which will give us 28 degrees. So that means that we have y equal to 28 e to the kt. Then we can use some other given information to find that constant k. We were told that the temperature after 30 minutes, or a half hour, was 61 degrees. So that means that the y value after 30 minutes is 61 minus 44, which is 17. So that means that we have 17 for our y value, equal to the function, which is 28 e to the k, but then instead of t, we have 30 minutes. So now we can use that to find out what k is, and that'll give us our actual function for y, which we can then turn back into a function for t. So this means 17 divided by 28 is equal to e to the 30k. We know what to do at this point. We're just going to take the natural log of both sides, which means ln of 17 over 28 is equal to 30 times k. So then we take the natural log of our fraction 17 divided by 28, and then divide that by 30, and that gives us approximately, again, a negative k value because we're talking about decay in this cooling instance, negative 0.023. 0.017 is approximately equal to k. So that means that our function y is equal to 28 e to the negative 0.017 times t. And then if we want to know what t is equal to, as in capital T, we're again just going to go back to y is equal to capital T minus 44, which means capital T is just equal to y plus 44. So our function for temperature is just capital T equal to 44 plus 28 e to the negative 0.017 t. So now that we have that, we're going to use that to find the answers to our two questions. Part A, what is the temperature at 60 minutes? This just means capital T of 60. And that would just be 44 plus 28 e to the negative 0.017 times 60. So then we can plug all of that in. 44 plus 28 times e to the negative 0.017 times 60. And that would give us approximately 54.1 degrees. And then part B, find the time it takes to cool to 50 degrees. So again, this means the temperature is 50, not the time. And we set that equal to 44 plus 28 e to the negative 0.017 t. And we just have to solve for t again. So we would subtract 44 from both sides. Divide both sides by 28, which would give us a fraction 3 over 14. Take the natural log of both sides. And then divide both sides by negative 0.017. So natural log of the fraction 3 over 14 divided by negative 0.017. Keep in mind that our answer is going to be in minutes, so this means approximately 90.614 minutes.